All right, so these two boxes are set up so that they've got a chamber here where we can actually have sound produced with this tuning fork. And again, when a tuning fork is set to vibrate, the tines move back and forth this way to create air pattern that's going to go into compressions and rarefactions. Now, both of these two boxes have the exact same tuning fork. So what we're really looking for is resonance. Now I'm going to set this tuning fork back here, and you can see that we've got the opening here. I'm going to set that so that it can catch some waves. And I'm going to take this box here and ring this tuning fork. So you can hear that, and then we've got that sound. But if I set it over here by this box and seal that off, we can still hear the sound because this one is now vibrating and resonating. So that's a forced vibration, and that's called resonance. All right, so we're looking at how tuning forks work. So if I think of the tuning fork as being something that's going to vibrate back and forth, when it moves back and forth this way, this is what we call the tines, when those move back and forth this way, it pushes air molecules into patterns where a bunch of the air molecules get pushed together and then they get spread apart. And we create this push together and spread apart as a way to kind of create that wavelength that we see. Now typically what we do is we start to look at this in terms of crests and troughs, so it makes more sense to us. So like this would be the point of a crest to go into a trough, into a crest, and into a trough. So we'd see something like this. And again, because this is kind of a vibration back and forth, we see these as standing waves, and that we would then have nodes and antinodes. Now to make a wavelength, we want to go from a crest to a trough, or from a compression through a rarefaction. So that's getting us the same kind of distance here. Now we see those gaps and those compressions. So this is what we call a wavelength. And a wavelength, if you remember, is just that upside down looking Y symbol. Now when we look at that wavelength, we say, well, that wave can go into an object like a tube that it could then force it to become resonant or force it to vibrate. So we say that the air column is going to vibrate. Now we have two types of tubes that we can use. We can have a closed tube, or we can have an open tube. And in all these cases, we start to look at how does this wave fit in here. Now, in a closed tube, we have to have the area at the top be open, so that creates like that antinode. Okay, but then at the bottom, it's going to create that node. And so what we would see is we would see that vibration pattern occur that would look very similar to seeing like this much of a wavelength. Now if we look at this, this is my whole wavelength. This is dividing it up. We can see this as 1/4 of the wavelength. So the length of the tube, however long the tube is only representing 1/4 of the overall wavelength. Now when we look at this in terms of an open tube, we're going to have that antinode area here, we'll have an antinode area here, we're going to have a node there. So really we're going to get an image that'll look like this, which if we look at that, that's that middle point there. So we see this end and this end and this end and this end. So we're really seeing half of the overall wave. So the length of the air column is equal to half of that wavelength. So that's kind of how we look at the differences between open tubes and closed tubes and when we see that resonance occur. Now So this is another tube that we can use to resonate. You can see that this one is open on both ends, and we're going to use a tuning fork, and we're going to make the air column inside of here vibrate. So this one, when we play it, if I adjust the length of the tube, we can get that stronger resonance point. But if the tube is too short, it won't resonate because it needs to be at the proper length for that frequency, just like I was showing in the notes.